As Cass was saying, my area is mainly in graphical models and computation statistics. The reason why we create graphical models is that we are providing language to design families of multivariate probability models. And we do this in a way that provides some degrees, some trade-offs in which you can design these families. We'd like our families to be flexible and to have some nice computational and statistical properties, such as being able to easily marginalize variables out of a multivariate distribution, be able to sample from. We also facilitate the statistical estimation of its parameters and structure. So we are used to that in general when people start modeling their models or Markov random fields or directly cyclic graphical models, and so on and so forth. So factorizations play an important role on designing these graphical models. But factorizations can be used in other contexts too, not only on density functions and mass functions, but also more recently there's the idea of applying factorizations to cumulative distribution functions. So this is not my idea, it's something that started relatively recent, independently from people in machine learning, people in statistics, and also people doing Copula modeling. So I spent some time here, what people are trying to accomplish when they try to design factorized forms of cumulative distribution functions. What are the implications of that? And I also want to spend some time relating that to more traditional graphical models, so you can have more of an understanding what's different when you pose factorizations directly in the CDF instead of the density function. My main contribution here is going to be talking about tractable Bayesian inference. Because you can imagine that if you're working with cumulative distribution functions, if you're working a high-dimensional problem, this should ring a bell, because if you want to do Bayesian inference, you need a likelihood function. It's not that straightforward to get a likelihood function out of a CDF. So I'm going to spend some time describing a contribution on how to do this tractable computation of likelihood functions, so we can embed that as part of a Bayesian approach. So the main target here of my presentation will be providing background and providing some computational techniques to deal with them. I won't cover much about conceptual questions on how to put priors or any detailed data analysis case here. It will be most focused on the computational aspects of it, with some toy examples in the end, just to illustrate how well these ideas can work. Okay, but more as a proof of concept than as a full-fledged application. So what do I mean about factorizing CDFs? Imagine you have a CDF which is expressed as a product of some factors. Sometimes people in machine learning engineering, they like to express factorizations using this notation here, a so-called factor graph, where each square here represents a particular factor, and the nodes linked to these factors are the arguments in each one of these. So you have a prevariate CDF function here, where it is expressed as a function of 4 factors. So how do you guarantee this product is actually going to give you a CDF? Well, this is some work that emerged in the machine learning literature at the Uncertainty on Artificial Intelligence conference. They show that by a sufficient condition for this product to be a CDF is that each one of these factors is itself a CDF. So it's not hard to understand why this is true, because all these factors being between 1 and 0, when imply the product is between 1 and 0. This being monotone, when imply the product is monotone too, and that's basically all you need to enforce that this is a CDF. Okay, so from now on, I'm going to assume that these factors themselves are CDFs, so my construction will always give you a CDF itself. So what kind of family this can build? This is relatively recent development, so there isn't much work there on trying to understand this from the point of view of giving physical interpretations for the parameters. So a lot of the work that people have out there on using these models is using them mostly as black box models for prediction problems. So from the point of view of black box models, these have some nice empirical advantages on predictive problems. So people have used this recently in spatial statistics, for example, compared to Gaussian copulas with some other sorts of Copula models to do predictions in a spatial field. But of course, only seeing this is predictive black box. So the types of shapes that sometimes you get can be quite different from the original parametric models. They have some degrees of freedom which you fit to the data. This gives you a predictive model. I'm not going to spend much time describing physical interpretations of these. Just imagine these as being viewed in a black box way. Okay? So this is just an example of what you get when you multiply two Gaussian CDFs. Then you get another CDF function whose PDF will have this episodic shape there with a kind of broke half moon, which for some data sets will provide a good fit. Okay? So why that is interesting from the point of view of modeling? Well, there's some nice computational properties when you see things from the point of view of CDF. One of them is easy marginalization. So you know you marginalize CDFs by just evaluating some of its arguments at infinity. So if you have a bivariate CDF here, you want its marginal distribution, evaluate one of the variables at its maximum possible value. This gives you the margin of a CDF. So if you have a factorization like that, and assuming each factor here is a bounded number of arguments, bounded as a function of the dimensionality, so you can assume it takes order of 1 to compute each one of these factors regardless of which margin they evaluate. So assuming that it takes order of 1 to calculate a factor, you can marginalize any high-dimensional distribution, paying a cost that is linear in the number of factors that we have. So for data that is very sparse, this gives you a model which is very easy to marginalize. Okay? And there's a relationship from the CDF factorizations to other graphical models, in particular models that emerge from marginalizing some latent variables. So suppose I have a model like this with 8 variables, where these are latent variables, 5, 6, 7, 8 are latent variables. I'm only interested in modeling the marginal distribution of 1, 2, 3, and 4. So after you marginalize the latent variables that you have there, you have some dependency structure over the remaining variables. The dependency structure that you have there is not a standard graphical model, because what this is representing here is some notion of marginal independence. So the lack of an edge in this graphical representation here means marginal independence. Okay? And despite the fact that edges here cannot be motivated by the fact that they're marginalizing some common latent parent in this directed graph. So these marginal dependencies, when you look at the point of view of parametric families, are translated into constraints in our parameterization. So if you have a Gaussian distribution, for example, which is Markov with respect to a model like that, marginal dependencies will be translated into structural zeros in the covariance matrix. So between 1 and 4 here, you have a marginal independence. So you have a 0 in the corresponding entry of the covariance matrix. So you can see this is a kind of dual of the Markov random field, where in the Gaussian case, we have these structural zeros in the inverse covariance matrix. And here we have zeros in the covariance matrix itself. So you cannot get around with a different graphical model to represent these constraints. It's a different type of graphical model. And this is actually one of the Markov properties of these properties of CDFs. Because for the sake of illustration, imagine you have just a pre-variant distribution like this. So you have your CDF here being given as a factor over x1 and 2, another factor over 2 and 3. If you want the marginal of 1 and 3, you're marginalizing 2 here by evaluating 2 at, say, infinity. You're just evaluating the CDF at the maximum value of x2. So this will decouple the factors in a function of x1 and a function of x3. So you have there marginal independence between variables which are not linked into the same factor. So one more way of trying to understand the properties of these products of CDFs is relating that to these models of marginal independence. Okay, it's one interpretation of them. And there are variations of this idea for other families, not only Gaussians, but also discrete distributions and so on and so forth. So this, I'm not going to get into detail here. There are ways of expressing marginal dependencies into other families other than Gaussians. Many models where you try to parameterize models of marginal dependencies, you usually get to the point where you have an explosion on the number of parameters. So there are approaches there that try to parameterize these discrete families, but they require, without getting into much detail, an exponential number of parameters there. So there are ways of just representing these independencies in any family by just taking account factorizations in the CDF. But the problem there is calculating the mass function out of the CDF. Okay? So if you have a CDF of a univariate distribution, for example, if you want to calculate this mass function, which is the difference between two levels of the CDF, we have two variables. What you have is an inclusion-exclusion formula. So to get this bivariate mass function from bivariate CDF, you have to do these calculations, which I assume all of you are familiar with. So if you want to calculate the PMF of a d-dimensional CDF, you have to do this inclusion-exclusion summations over an exponential number of terms of your CDF function. So in general, this is intractable. When you impose some extra constraint here, you'll see that this calculation can actually be done by some efficient methods that I'm going to get into detail soon. So let's just skip this thing here. In terms of yet another point of view, people have also developed the same idea of product of CDFs into the Copula literature by a completely independent group of researchers. So they realize they can build copulas out of product of copulas too, which is an interesting construction because it's not that straightforward to build an arbitrary dimensional copula function. If you were to do that by starting from scratch, it would require knowing, for example, it would require knowing what the original CDF of a model was. You'd have to rewrite this original CDF, make explicit the marginal CDFs and the inverse CDFs, so that it became from any arbitrary CDF a particular copula function by identifying what the univariate CDFs of this function were originally. And this is not an easy recipe because this is not in general easy to find these marginal CDFs from some arbitrary distribution. So it's not that straightforward to build an arbitrary dimensional copula. So what some people have done in the Copula literature is to define a simple construction where from a product of copula functions you can get a copula tree. Okay? So it's again a product of CDF representation. There's a tiny catch there that the product of copulas is not really a copula. You don't have univariate, you don't have uniform 0-1 margins in that case. But there are ways around of that which I'm not going to get into detail here, where you can do some transformation in each one of the factors so that what you'll obtain in the end is indeed a copula. Okay? So these are several different points of view in which you can interpret a product of CDFs. Now the difficulty here, as I said, is to do things like parameterization. Because as I illustrated in the discrete case, in general you have an exponential number of terms that you have to calculate in order to get a mass function out of a CDF. So if you're doing Bayesian inference, you cannot even calculate the functions that you need to do MCMC, for instance. You cannot even do MCMC if your likelihood function is intractable. So what can you do in this case? Well, this is an idea that we exploited in the literature and try using dynamic programming for things like that. Okay? So suppose you have a chain like that. So it's just that bivariate representation that I mentioned to you. You can represent the CDF of this chain as a product of CDFs over the edges of this chain. Notice here I'm using already some sort of copula representation, but just for the sake of illustration, I'm showing how to get a copula out of a product in a chain. So adjustments like this are necessary if you want to get a Copula function out of this product. But suppose I just give to you this product of CDFs. How do I get the density function of this Copula? Well, we can apply the chain rule, we can apply the product rule here to differentiate this with respect to each one of the arguments. So differentiate with respect to U1 in the first factor, it will be fine, U1 doesn't show up anywhere else. Differentiate with respect to U2 in the first factor, but not with respect to the rest. Then you add the differentiation of the second set of factors here with respect to U2, but not with respect to the first factor, and you iterate that. So you apply again the product rule within each one of these factors here. So this is a type of dynamic programming procedure to do differentiation instead of integration. Okay? This will be fine for chains and generalizations of that for networks of any particular structure using a trick that is completely analogous to what you do in Markov random fields. You can build a junction tree, and you can build this sort of message passing scheme or dynamic programming scheme to differentiate with respect to each one of these vectors. And the algorithm is very, very confusing. This is just what people have published before. This is what you need to do, but it's very complicated to implement, it's very complicated to generalize. So one thing you can do here is to understand that this representation that you have there can be cast in a message passing scheme that is not only analogous to what you have in Markov random fields, but it's identical to what you have in Markov random fields by using a different interpretation of these steps. So you can, for example, write the product rule with respect to indicators that tell you which factors, on which factors each of the variables are being differentiated on. So we apply the product rule, basically saying, for this term, I'm differentiating this factor with respect to this variable, and so on and so forth. And of course, this is just a textbook formula for the product rule in general. And one way of interpreting this is looking at this formula and realizing that what we have here is some sort of augmented latent variable representation of the original CDF in terms of a joint distribution of differentiation factors and the original variables. So Z here representing which factor is being differentiated with respect to which variable. So if you want to have the PDF with respect to U here, is the equivalent of summing over all possible values of Z. So what you have here, some sort of marginal of a latent variable model. So you can have now, you can write this now some sort of augmented space where you augment your original representation with indicators that tell you with respect to each factor, each variable is being differentiated to. Okay? So to calculate now the density function of them, or the mass function of these variables, just sum over these differentiation indicators. This is particularly nice because you can use the standard black box methods for doing junction tree inference in Markov random fields directly to this problem without any modification. So you don't need to completely create from scratch inference methods to calculate likelihood functions in these methods. Not only that, but some problems where you have dense representations, where you have dense graphs, you can't even do dynamic programming to be able to calculate the likelihood function. You cannot do message passing because you do have some large factors in a problem. But since you have this representation here, you can imagine this as some latent variables that you can include as part of a Markov chain Monte Carlo procedure. So you can do a joint Bayesian inference representing these as latent variables that need to be sampled. So you can do proposals that include not only sampling parameters from the posterior, but at the same time, you'll be sampling these variables as if they were latent variables in augmented representation. So all of this comes for free to you without having to reinvent the wheel with new computational techniques. You just reduce the problem into a problem of inference on these latent indicators. It's also an interesting way of linking the problem of doing MC for integration with MC for differentiation, which is essentially what you're doing here. So if you have a discrete problem, it's slightly more difficult because, as I mentioned to you, in the discrete case, we have not the total rule for differentiation, but we have this expression in terms of differences. And here you see some negative terms. So you cannot pretend these variables form a joint distribution with your original variables because the terms that you have here can be negative. So you don't have this interpretation of the discrete case as having a joint distribution over difference indicators and the original variables. But one thing that you can do using a Copula formulation is to parameterize your problem in terms of a copula, which is always continuous. So you can create your model directly in this continuous space using a copula and project it back to that discrete space where we're using the standard techniques of Copula modeling. So you can still solve everything in the continuous space using this interpretation where there is an actual joint distribution because everything here is non-negative. Okay? So there are other latent variable interpretations besides this one I give to you. I don't have much time to get into detail. I'm just going to skip to one simple numerical example, but this is just one way by which you can reduce this product of Copula's problem, or product of CDF's problem, into an augmented latent variable model. Okay? But in the paper, I described some links between these bidirected models or product CDF models with DAG models with latent variables, which is an alternative representation. So let me just skip to one simple numerical example. So here, you have just a simple model which is a 5-dimensional chain. So you can actually use dynamic programming data to calculate the likelihood function because it's a very small dimensional problem. And what I'm going to do here is just to compare how well this latent variable formulation, which takes the difference indicators as if they are latent variables, compared to an approach where I'm calculating the likelihood function using dynamic programming. Okay? So these are some, you know this panel here. These are some examples comparing a given sampler that marginalized the likelihood function using dynamic programming. And this is a given sampler where the difference indicators are included as if they are latent variables and sampled by given sampler. So here in this simple example, we've got an effective sample size, which is about 5 times smaller than the effective sample size that you get by marginalizing the likelihood function analytically, which is a good illustration that this has some potentials to work in practice, because each iteration here is potentially much cheaper than each iteration there, because here you're not evaluating a summation over all the possible differentiations of the vectors. So evaluation here is relatively cheaper in general than calculating the likelihood function by dynamic programming. Okay? So there are many other more results on that. We're very happy to discuss with you afterwards. But this points out to another way of building multivariate distributions in a way that you can use your standard tools already, straight out of the box, to tackle these problems, which people didn't realize before. And they're trying to come up with some novel algorithms that by the end of the day will not necessarily reduce those problems into a latent variable formulation. Okay? So this is my main message, and I'll be happy to take any questions.